Section 3.6, prove theorems about perpendicular lines. So this will be our last section for chapter 6, and our goal is to use theorems with perpendicular and parallel lines. So to start, theorem 3.8, this one just doesn't have a name. It says if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So we'll have here line G and line H and angles 1 and 2. And basically this says if angle 1 is congruent to angle 2, then G is perpendicular to H. Theorem 3.9, perpendicular lines intersect to form 4 right angles. This is one we use a little bit more. And so we're going to draw ourselves a pair of perpendicular lines. And we'll draw the box here to show that they are perpendicular. And we'll also label the lines, R, J, and K. And we'll say if J is perpendicular to K, then angle 3, angle 4, angle 5, and angle 6 are right angles. In theorem 3.10, if the sides of two adjacent acute angles are perpendicular, then the angles are complementary. So this one reads, if ray YZ is perpendicular to ray YX, then angle 7 is complementary to angle H. Alright, so we are given a proof here. It says given angle 1 and angle 2 are complementary. So given angle 1 complementary to angle 2, we're trying to prove that the sides are perpendicular. So it's kind of the opposite of theorem 3.10. So we're trying to prove the converse of theorem 3.10, if you will. So we go through, what does it mean to be complementary? Well, it means that the measure of those two angles add to be 90. So we will say that measure of angle 1 plus the measure of angle 2 equals 90 degrees. That was our definition of complementary. Okay, we are in terms of angle 1 and angle 2, but we need to get in terms of BA and BC. So we need to have this conversion factor, if you will, between the numbers and the sides. Well, what did the angle 1 and 2 also add to make? Angle ABC. So what we are going to say next is that angle ABC equals the measure of angle 1 plus the measure of angle 2. That was our angle addition postulate. And what does that do for us? Well, we have that the measure of angle 1 plus the measure of angle 2 is 90. and that angle ABC is equal to measure of angle 1 plus measure of angle 2. So we will say that angle ABC equals 90 degrees. Why? Because we substituted. You could also say transitive property. We'll just say substitution. So we have measure or that angle ABC is 90 degrees. What does it mean to be 90 degrees? It's a right angle. So we will say that angle ABC is a right angle. Why can we say that? Well, it's the definition of right angle. If it's 90 degrees, it's right. It's right. So that was def of right angle. And finally, what does it mean to be a right angle? Well, what's the connection between right angle and trying to get to perpendicular? Our definition of perpendicular is that they intersect at a right angle. So we will say that BA is perpendicular to BC by the definition of perpendicular. If we have a right angle and they intersect at a right angle, obviously they're perpendicular by its definition. All right. A couple more theorems we have yet in this section. The perpendicular transversal theorem, which states if a transversal is, we'll call it A, is perpendicular to line B, then A is perpendicular to lines parallel to line B. And what we're going to do is we're also going to write this symbolically. And we're going to say if A is perpendicular to B and B is parallel to C, then A is perpendicular to C. So what's going to happen is you're going to have a pair of lines, B and C, that are parallel to one another. And we're going to drop a transversal in here such that it's perpendicular to B. If it's perpendicular to B and these lines are parallel by the corresponding angles postulate, we know that this is also going to be 90 degrees. That's what this theorem is stating. Lines perpendicular to a transversal theorem. So if they're perpendicular to the same lines perpendicular to the same transversal are parallel. That's what this theorem is stating. So lines perpendicular to the same transversal are parallel. So what we will do is say if G is perpendicular to K and H is perpendicular to K, then G is parallel to H. So you're going to have a line here, a transversal K, and you're going to have two lines, G and H. And if they're perpendicular to the same line, well, as we can see here, corresponding angles converse would say that those two lines are parallel. That is what is going on in this theorem. Our last example. Determine which lines, if any, must be perpendicular. Explain. Well, we can see right there we have the perpendicular box, so that means B is perpendicular to D. Explain. It's marked on diagram. Okay, so B was perpendicular to D, and that was given on the diagram. All right. Any others? Well, we can see here that these are clearly marked to not be right angles here and here, so those are not perpendicular. But what they are is marked to be congruent. They're both a single arc. And these are corresponding, so A is parallel to B. And by the perpendicular transversal theorem, if it's perpendicular to one of parallel lines, it's perpendicular to the other. So A is perpendicular to D. And explain, A is parallel to B by the corresponding angles converse, we'll say postulate converse. And since B is perpendicular to D by the perpendicular transversal theorem, A is perpendicular to D as well. So since we have parallel lines and it's perpendicular to one, it's perpendicular to the other.